Now that we have seen the Fourier spectrum of Boolean functions, let us move on to spectral analysis of periodic functions, in particular discrete periodic functions. And let us begin with an overview of how we will approach this topic. First, we will look at periodic functions with some examples, and these are going to be continuous functions. We will look at the Fourier expansion of such periodic functions, and based on the Fourier expansion, we will define the Fourier spectrum for periodic functions. After we have an understanding of the Fourier spectrum for continuous periodic functions, we will move on to discrete periodic functions, which are essentially such continuous functions sampled at discrete points in time. And we will extend the notion of the Fourier spectrum to these discrete periodic functions. Notice that these discrete periodic functions are essentially vectors based on their sampled values at, say, the n discrete points. So, there will be a natural analogy between Boolean functions, which are also vectors, and these discrete periodic functions. So, we will view Fourier spectrum as essentially being a transformation of the vector from a standard basis, whether it be Boolean functions or discrete periodic functions, to an alternative Fourier basis. In the context of Boolean functions, the Fourier basis would be the parity functions. In the context of discrete periodic functions, the Fourier basis will comprise of suitably defined sinusoids. Let us now understand periodic functions. Well, what is a periodic function? It is simply a function that repeats its values in regular intervals or periods. So, we have an example shown in the slide here. This function repeats itself every time the period cycles. Of course, we are all familiar with some very standard periodic functions. All the trigonometric functions we have learned from high school days are essentially periodic functions. We are talking about functions like sine, cosine, and so on. And they typically have a period that of interval 2 pi radians. In addition to these standard periodic functions, a lot of real world signals, radio wave signals and so on, are also periodic in nature. And in fact, these periodic functions are really what drives the area of digital signal processing, and a lot of the applications in digital signal processing would require a careful interpretation of signals as periodic functions. Now that we know what a periodic function is, we ask, what is the Fourier spectrum of a periodic function? And to understand that, we will need to first notice that any periodic function can be expanded and written as a linear combination of sine and cosine terms. This representation is called the Fourier expansion of a periodic function. So, as shown here, the periodic function s of x is begins with a magnitude term a0 divided by 2, followed by an infinite sum of sine and cosine terms. Now, each of these, as we increase the j value starting from 1 on to infinity, the frequency of the appropriate cosine and sine terms increases. And each of these sine and cosine terms themselves have coefficients uppercase A sub j and uppercase B sub j, and each of them uppercase A sub j is equal to lowercase a sub j times sine phi j, and similarly uppercase B sub j, notice, is equal to lowercase a sub j times cosine phi j. These phi values can be interpreted as phase shifts, and using the standard trigonometric formula of sine a plus b equals sine a times cosine b plus cosine a times sine b, we get an equivalent form for this Fourier expansion given by S of x equals a sub 0 divided by 2 plus an infinite summation where we only have the sine term, however, the sine term with an appropriate phase shift for each of the j values. In this expansion, the first few terms are far more important than subsequent terms. So, let us look at an example. This is a square wave, this is a periodic function, and we would like to represent this periodic function using its Fourier expansion. Now, if we are allowed only the first sine wave, then we would get an approximation of the square wave as shown here. The sine wave has the same period as the square wave, and to a large extent has the same structure. And so one can say that the sine wave approximates the square wave, but not as nicely as we would like it to. However, if we include the second sine term, then we get a significantly better approximation of the square wave, and including a few more sine waves, we get a better an even better representation of the square wave using just the sine terms. And notice that as we use more and more sine terms, we reach a certain point at which the Fourier expansion using the limited first few terms itself becomes a good approximation of the original function, in this case the square function. So, this illustrates the importance of the first few terms in the Fourier expansion. And in general, the coefficients in the Fourier expansion is called the Fourier spectrum of the periodic function. Consider this particular, the first few terms of the Fourier expansion of the square wave. Notice that this is obtained as the sum of several sine terms. Let us look at it in more detail, and we will look at it from a slightly different perspective, and towards that this diagram is helpful. And in this figure, the individual sine terms are separated out, and you will notice that the first sine term has a significantly higher magnitude, the second sine term has a smaller magnitude, and the third sine term has an even smaller magnitude, and so on. These magnitudes of the sine terms are essentially the spectrum, the Fourier spectrum of the square function. Of course, the square function will have an infinitely long Fourier spectrum because the Fourier expansion is an infinite series. However, the first few terms are the most important terms, because once we have the first few terms, the Fourier expansion approximates the square function quite well. So, here is a figure representing the Fourier spectrum of the square wave, and often this is called the frequency spectrum simply because this represents the magnitude of the various frequencies of the sine terms appearing in the Fourier expansion. While signals can best be represented as continuous periodic functions for intuitive reasons, the continuous periodic functions are not suitable ways to store and process information. It would be better if the information is stored as a discrete vector, and for this purpose continuous periodic functions are often sampled at discrete points in time, and their sampled magnitude values are stored as a discrete periodic function and are processed in that manner. This makes a lot of sense, especially when we use computers to store and process signal information. So, the natural question one would ask is, how many samples do we need per period, or what is the frequency with which we should sample a periodic function in order to capture the required amount information about a continuous periodic function. To capture it to capture the information perfectly, we may need a lot of samples at a very high frequency. However, if we know that a particular signal is sparse in its frequency spectrum, then there are some very strong theorems that say that the number of discrete samples required to capture most of the information about a periodic function is quite small, and these are typically theorems such as the Nyquist-Shannon theorem. And once we have an understanding of the sparsity of a particular signal in the frequency domain, that will indicate to us the length the number of samples, and therefore, the length of the vector used to represent discrete periodic functions. Here we use the letter uppercase N to denote the number of samples sampled values in a period. Recall that the Fourier transform of a periodic function requires an infinite number of sinusoidal waves. So, the Fourier spectrum will be infinitely long because the Fourier expansion is an infinite sum, and the Fourier spectrum comprises the coefficients in the Fourier expansion. However, in the context of a discrete periodic function, we have the discrete periodic function, however, is a vector of dimension n. So, the frequency domain can be viewed as an alternative basis, and therefore, the number of points in the dimension of the frequency domain is also around n. This would imply, thanks to the sampling theorems like Shannon and Nyquist-Shannon theorems, that the number of samples actually required in order to capture the information of a periodic function in discrete points in times is actually small. So, just twice the number n would be sufficient in most cases. So, now that we understand periodic functions and in particular discrete periodic functions, their Fourier spectrum and also the Fourier spectrum of Boolean functions, we can work our way towards an analogy between Boolean functions and periodic functions. In particular, we are talking about discrete periodic functions. Let us assume that we have a periodic function like the way a simple sine wave as shown here, and let us assume that we have sampled this periodic function at uppercase n discrete points. So, each of the sampled point taken in sequence can be denoted by the index 0, 1, 2, 3, 4 and so on up to n minus 1. And when we represent each one of these indices by their binary values, we get we see that a 3-bit representation in this context where uppercase n equal to 8 is sufficient. So, if you notice, there is a natural analogy between these discrete periodic functions and Boolean functions. For discrete periodic functions, we have these indices ranging from 0 to n minus 1, and these indices can be written, can be encoded as inputs into a Boolean function, and the function can be evaluated based on this particular signal. So, for example, this discrete periodic function can be represented as a Boolean function if for each of the inputs, say 0, 1, 0, we assign the output equal the magnitude of this periodic function at that sampled point. Extending this analogy, we can see that the notion of spectral analysis, Fourier spectrum, Fourier basis and so on extend and include both Boolean functions and discrete periodic functions. So, let us look at this a bit more carefully to establish this analogy. We have already seen that Boolean functions form a vector space of dimension 2 power n, where n is the number of bits in the input vector. And similarly, a discrete periodic function is a vector space of dimension uppercase n, where that n is the number of sampled values in a period. And if we look at the at this figure that builds this analogy between Boolean functions and periodic functions, we notice that a period in the context of discrete periodic functions is going to be uppercase n, but if that is encoded as 2 power n points at which we sample the periodic functions, then the Boolean function can be viewed as having a period of 2 power n. Of course, the Fourier basis for each of these vector spaces different. For the Boolean functions, we used parity base functions as the basis functions. For discrete periodic functions, however, we used sinusoidal functions. And what is the Fourier spectrum? Well, the vector, notice that recall that the Boolean function itself is a vector. Its representation in the parity basis would be the Fourier spectrum. Similarly, the coefficients in the Fourier expansion of a discrete periodic function would be its Fourier spectrum. and both of these have the same standard basis. For example, in the Boolean functions, for each of the 2 power n inputs, we will the evaluation of the function at those inputs will be the standard basis, the representation of the vector in the standard basis. And similarly, for the discrete periodic functions, we have uppercase n number of sampled points, and the magnitude of the periodic function evaluated at those uppercase n number of sampled points is the vector represented in the standard basis. One more analogy between these two functions, Boolean functions and discrete periodic functions, is that a lot of the real world examples tend to be sparse in the Fourier basis, in the sense that the number of non-zero terms, the terms that matter in the Fourier basis is often very few. This is particularly true in digital signal processing, where the periodic function of a signal, when transformed into the frequency spectrum, would be quite sparse, even though the original standard time domain representation of the function may look quite complicated.